Yeah, we're definitely going to get triggy with it. Ha! Puns. All right. Let's start with questions from you guys. I think last time we covered up through section 2.3. I signed up to problems 44. Does anybody have any homework questions going on? Cheyenne. 19. Okay. Oops, that's the wrong set of problems. You know what I think I need to do here? I need to reshuffle the stuff in the content library so the new stuff is on top. Maybe we'll do that next week. All right. 19, it says 2 concentric circles cut by the same angle. So circle 1, circle 2, those are circles, right? There's that same angle. So we have a radius for the smaller circle, oops, why would I use S there? A radius for the bigger circle, an arc for the smaller circle, an arc for the bigger circle, but they're both going to have the same theta, right? We're told that R1 is 4.3. We're told that S1 is 5.2. Then we're told that R2 is 5.2. We're told that S2 is what we're looking for. So what I'm going to do is I'm going to take this information and say that S1 is equal to R1 times theta, or 5.2 is equal to 4.3 times theta. So if I divide both sides by 4.3, I get my value for theta. Cool with that? Using that now, I can plug in down here. So S2 is equal to R2 times theta. So I have S2 is equal to 5.2 times 5.2 over 4.3. That's my value for theta from before. And then we just plug them in, and that'll spit out my answer. I'm going to let you guys do the calculator part. Does that feel okay, Cheyenne? Okay. What else? Yo, Matt.
Could you do 23?
Sure. So this one is going to be just like the example from the notes. So it says, Danny's riding his bike that has 22-inch diameter wheels. He can ride at 14 miles per hour. How many revolutions per minute are his tires making? So this is just like a straight unit conversion problem. So I'm going to be taking miles per hour, doing some unit conversion, and asking to end at revolutions per minute. Well, first thing I should notice is that I'm in per hour. I want to end up in per minute, so let's just do that time conversion straight away. I know 1 hour is 60 minutes. Now I'm in miles per minute. Somehow I got to convert miles into revolutions. The trick there is remembering that 1 revolution is equal to 1 circumference. So in our case, the formula for circumference, since the wheel is a circle, is just 2 pi r, or pi times diameter. So my diameter was 22 inches, so my circumference is 22 pi inches. The problem, though, is that my unit for distance is in miles, not inches. So before I can apply that conversion factor, I got to convert miles to inches. Oh, man. Well, I remember that 1 mile is 5,280 feet. And I remember that 1 foot is 12 inches. And now I've converted miles to inches. So I can use my last conversion factor here. That 22 pi inches is 1 revolution. And now I'm in revolutions per minute. Yay! And all you gotta do is grind through that multiplication there. Is that cool, Matt?
Yeah.
So almost the same problem as from the notes. It just, instead of getting revolutions per second, we got revolutions per minute. But I approached it identically, right? NBD. That's short for no big deal. Anybody else? Cool. Today, section 2.4, which is a good one. Let's get after it then, folks. All right. So remember what we did last time in section 2.3. We came up with this standard position definition for an angle, where I put the vertex of my angle at the origin. I draw the initial side on the positive x-axis, and then I rotate that terminal side that many degrees, starting at the initial side, going counterclockwise if I have a positive angle and clockwise if I had a negative angle, right? Everybody's cool with that? All right. Now imagine that I have some point P anywhere on that terminal side other than where the at the vertex, right? Since the vertex isn't just on the terminal side of the angle, it's on both the initial and terminal side. Okay, so I'm going to pick some point there. I'll call it xy. What can I do with that? Well, I can turn that point on the terminal side into a right triangle by just kind of dropping a perpendicular. Everybody kind of see that? So what should I, what should I write for the side length here that I've highlighted in yellow? Ryan? Great, so I'll call it x. And what should I name this side here that I've highlighted in green? Y. Everybody's okay with this? To graph the point, we go x over and then y up. So the side length on the bottom on the x-axis should be the same as the x-coordinate for my point. And the vertical side of my triangle should be the same as the y-coordinate for my point. Everybody's cool? How would I find the third side of that triangle then? The Pythagorean theorem, right? It's going to be the square root of x squared plus y squared. Now that's kind of a mouthful, so I'm going to just abbreviate that with the letter R. Everybody's okay with the picture I've drawn here? Note that r also represents the distance from P to the origin. Everybody's agreed with that? Okay. All right, so if I use this drawing, sine theta would be equal to opposite, which is y, over hypotenuse, which is r. Cosine would be adjacent, which is x, over hypotenuse, which is r. Tangent would be opposite, which is y, over adjacent, which is x. Cosecant would be hypotenuse, which is r, over opposite, which is y. Secant would be hypotenuse, which is r, over adjacent, which is x. And cotangent, which would be adjacent, x, over opposite, y. And what have we done here? This is sine, cosine, tangent, etc., defined by a point on the terminal side of a standard position angle theta. Aha! Now, recall again from last time, what kind of angles can I draw using the standard position method? What size of angles can I draw with that? More than just a cube. I could draw angles of any size, right, from negative infinity to positive infinity, using that standard position method, because I just keep spinning either clockwise or counterclockwise, and can draw an angle that is that size. Everybody's okay with that? You remember doing that yesterday? And now, because my sine, cosine, and tangent are built off coordinates on the terminal side of a standard position angle, what kinds of angles can I do sine, cosine, and tangent on? Any angle I want. What? That's exciting. We have just broken the shackles of geometry. We're no longer restricted to using sine, cosine, tangent, etc. on acute angles from a right triangle. We can now use those functions on angles of any size. That's exciting, guys. Let's do a couple of examples to kind of illustrate how exciting that is. So let's say that we have the point 3, 4, and it lies on the terminal side of our standard position angle theta, and we want to find the 6 trig ratios for theta. Well, I guess let's start by drawing ourselves a picture. I'm going to plot -3, 4. Guess I would plot that. So one possible theta could be this guy right here. Why did I say one possible theta? What other theta could I have drawn? Well, there's infinitely many that I could have drawn. But the point is, anything that I would have drawn would have to be coterminal to this one. So whether I went around once and then ended up there, or I went backwards and ended up there, it doesn't really matter, right? They're all going to have the same values for sine, cosine, and tangent because the terminal side is in the exact same location. So far, so good? Okay, I'm going to get those marks out of there. If I go in and draw in my triangle, I know that the x side should be the same as the x coordinate, and the other side should be the same as the y coordinate. We called that side r. How did we find r again? Pythagorean theorem. Little word of caution here when I'm doing this. If you're using your calculator to do this, you got to be a little bit careful how you're typing in -3 squared. -3 squared should be the same thing as -3 times -3, correct? Which would be +9. Okay, so I type -3 squared into my calculator. Uh-oh. Why did I get -9, Mr. Gulag? Because you didn't type it into your calculator correctly, student. This is what you mean. You want to make the 3 negative and then square it. The calculator is going to strictly follow the order of operations. Making something negative happens in the multiplication step of the order of operations. So if I typed in -3 squared with no parentheses there, it's going to square first and then make the answer negative. You want to type it in this way where we've made the answer negative and then squared it. Basically, it needs to look the same as what I type on my sheet of paper. Just as a heads up, that the calculator is just going to do for you what you ask it to do, not what you mean for it to do. So if you tell it to do the wrong thing, it's going to just do the wrong thing on you. All right. So I now have the values for x, y, and r. Everybody happy? Okay. So sine should be y over r. Cosine should be x over r. Tangent should be y over x. Cosecant is the reciprocal of sine. Secant is the reciprocal of cosine. And cotangent is the reciprocal of tangent. So I'm done. Neat. So let's do another. Let's find the cosine of 150 degrees without the calculator. But Mr. Kulik, 150 degrees isn't an acute angle. Student, we just defined sine, cosine, and tangent on any angle. Don't use the right triangle definition here. Use the new definition that we just created. All right. So we'll start by drawing our standard position angle. So 150 is over here. How do I know how far to go, Mr. Kulik? Well, each quadrant is how many degrees? 90 degrees, so I went 90 degrees. That leaves me 60 to go to get to 150. 60 is more than half of 90, so I just went somewhere a little bit more than halfway. Just eyeballing it. When Mr. Kulik's looking at your angles that you're going to draw, that's all he's doing. You're just making sure that your angle, your terminal side's in the correct quadrant, and then it's at least on the right side of halfway. The correct side of halfway, I should say. You know what I mean? Because what would look like the difference between like 150 and 155? I don't know. Mr. Kulik couldn't tell the difference just by looking at them. Unless you had to have them both on the same axis, then like one should be further than the other. But, you know, whatevs. Okay. So there's my 150 degree angle. I'm going to pick some point here on my terminal side. I'm going to draw my right triangle. What does this angle down here have to be? It's a simple geometry question. Should be able to do this in your head. How far did my initial angle go? 150. How far is it back to the x-axis? 180. So what's the piece that's missing there got to be? 30. Everybody agree? Oh, so this piece over here has to be 60, and we're living in a 30, 60, 90 triangle. Oh, these guys again, Mr. Kulik. All right. The ratio of side lengths in a 30, 60, 90 triangle, the short side, I'm going to use the letter A here rather than X to represent that value. I didn't want to use X because there's an X coordinate also rattling around. I felt like I was going to be abusing the notation a little bit. So I'm just going to use like an A or something here. So it's A root 3, and 2A. Everybody's okay with that? But I hate that these little A's are rattling around in here, don't you? So tell me about this point P that we picked. Did we have any restriction on where we could pick P on the terminal side? Did I pick that P any certain kind of way? No. I just pick it wherever I want it to be, right? Everybody agree with that? So you know what I'm going to do? I'm going to pick it so that A has a specific value. What value of A do you think I'm going to pick my P to so that A is? What's the easiest value of A could be? 1. Yeah, I'm just going to pick my P so that my A is 1. So this just becomes 2 instead of 2A. A just becomes 1, and the other one just becomes square root 3. Oh! That's easy. Does that all look good to you guys? Does that triangle look correct? Correctly labeled? You should answer no, Mr. Kulik. Oh no, what's the problem? What quadrant are we in right now? Quadrant 2, right? This was, remember back in Algebra 1, how we named the quadrants? In quadrant 2, well, in quadrant 1, the x's are positive or negative? Positive. And the y's are positive. In quadrant 2, the x's are positive or negative? Right, because we're going to the left to get into quadrant 2, so the x's have to be negative, but the y's are positive. In quadrant 3, the x's are, and the y's are, great. And in quadrant 4, the x's are, but the y's are, great. So, if I do that, what do I have to update here? Has to be negative square root 3, because that needs to be the same as the x coordinate on my point P. Woof! Mr. Kulik. But that's it, dude. We did it. So now we have everything we need. So the problem was asking us to do cosine of 150. So that's just going to be x over r. And we're donezos. Oh. Well, drawing the picture was kind of tricky, but not even that bad. Just boiled down to seeing another one of these stupid 30, 60, 90 triangles that I'm sick of. Is everybody happy with what I did? Okay. One more step in our definition. So notice that the way we've defined sine, cosine, and tangent right now, where we're just picking some point on the terminal side of our standard position angle. So conceivably, if, Luke and I were both doing cosine of 150, I could pick one point P and he could pick a different point P, right? It's kind of a hassle that we're all picking different things. Let's standardize this process so that we're all going to pick our point P the same way. Sound good? The way we're going to choose our P is so that it's always the same distance from the origin. What do you suppose we're going to choose that distance to be? What do you think? What would be a good distance from the origin to pick P as? I mean, how about 1? Right? Let's not get cute about it. So as a result, when we had sine of theta as y over r, this now becomes sine of y over 1, or sine is y over 1. So just y. Similarly, cosine theta, which was x over r, now becomes x over 1, or just x. Cosecant theta, which was r over y, now becomes 1 over y. Secant, which was r over x, now becomes 1 over x. But remember, tangent was y over x. That doesn't change at all. And similarly, cotangent was x over y. So that doesn't change at all. But it was okay with this update? Now let's think about this. If I consider all possible standard position angles, and I want to look at all possible P's from those terminal sides of those standard position angles. So one P could be, say, here, where it's 1 unit from the origin. Everybody okay with that? Another P could be here, and here, and like there. And oh my goodness, Mr. Kulak, what shape am I creating? If I look at where all the P's could have been. Oh, come on, guys. What shape is this? It's a circle. And what's the radius of this circle? How far is each of these points to the origin? 1 unit. So the radius on the circle is 1, right? That's right. That's just 1 there. So it's radius 1. We have a special name for this kind of a circle. We call this a unit circle. So each of these points is like our P, right? Any of these P's would be a point on the terminal side of some angle theta. But look up above. What is sine theta the same as now? Y. And what is cosine theta the same as? X. So my point P is really cosine theta, comma sine theta. Oh! This is my third now definition for sine, cosine, and tangent, etc. Well, that's really pretty cool. Hold on one second. I need to copy something in real quick. So we're almost done with 2-4. Exciting. I want to make one more observation. Let's go back to this example where we did the cosine of 150. What we noticed is that if this angle, when we draw that angle, forms a reference triangle, that's what this triangle is that we built. It's called a reference triangle. If that reference triangle either forms a 30, 60, 90 or 45, 45, 90 triangle, we'll be able to compute the values for sine, cosine, tangent, etc. exactly without a calculator, just by using these 30, 60, 90 and 45, 45, 90 triangles, right? What we are going to do now, so we're going to do that calculation just one time, record all that information so that we can reference it later, so that we don't ever have to do these calculations again. Everybody's okay with that? So this piece that I just dropped into the content library that's called unit circle blank, we're going to fill out together. I just pushed a sync on my notebook, so if you're want to follow along on your own, you're welcome to do that. But I'll have a completed version in your, in your OneNote, and you won't ever have to do this process again on your own. We'll just use this tool, but I think it's helpful to kind of see how the tool is constructed. Okay? All right, so I'm first going to go through and label some of the angle measures. So if this is my point on the terminal side, what measure of angle is this if this is my initial side and also my terminal side right here? That's a 0-degree angle, right? What is the coordinate of this point gotta be if this is a unit circle? How far did I go to the right? 1 unit. And how far did I go up? 0 units. So that's the point 1, 0. Okay, let's move up to this spot up here. What is this angle's measure going to be? 90 is correct. Go ahead and shout them out if you know it. Okay. What is that? What is the point there at for that P? How far did I go over? 0. How far did I go up? 1. Everybody's cool? What is this angle going to be? How far is that? How many degrees? It's a straight line, guys. 180. And what is that? What's the coordinate at that point going to be? -1, 0. What if I'm talking about this angle here? What's that got to be? $270, right? And what's the coordinate? Well, 0, -1. Everybody happy so far? Okay. Let's do the 45, 45, 90 reference triangles. So I'm going to draw in all the angles that make a 45, 45, 90 reference triangle. So like that's the 45, 45, 90 triangle I'm talking about right there. Everybody's okay with that? I'm going to draw it off to the side here. Remember that the ratio of side lengths in a 45, 45, 90 triangle is A and A root 2. Now, this side of my reference triangle has to have what length? What does that length of that side have to be? We're in a unit circle. That side is a radius, so it has to have length 1. Everybody's okay with that? So if I solve for A, I divide both sides by the square root of 2. So this side would be 1 over square root 2. And this side would be 1 over square root 2. Remember that this side is my x, and this side is my y. So this point here would have coordinate 1 over square root 2, comma, 1 over square root 2. The next place where I can form a 45, 45, 90 reference triangle is right here. When I do that, the x and y coordinates are going to be the same except for possibly them being positive or negative. Since we're in, what quadrant is this terminal side in, or what the point on this terminal side? What quadrant is this in? Q2, right? In quadrant 2, the x coordinate should be anybody, please try to participate. Just anybody? Negative, right? Because you're going to the left. Everybody remember that? So I know that that's going to be negative, and in fact, I'm just going to go ahead and write the negative sign in front of all the x coordinates in that quadrant, just so I don't forget to do it later. And then I know that's going to be the same 1 over square root of 2 from the previous one. And the y coordinates in the second quadrant are also positive. So there's that. Okay. The next place where I can build a 35 or 45, 45, 90 triangle is down here at 225. So like we're talking about that reference triangle there. In the third quadrant, the x's are positive or negative? Negative. The y's are positive or negative? Okay. And then I'll just copy in the same values otherwise. And the last place where we can build a 45, 45, 90 reference triangle is here at 315. This is the fourth quadrant. In the fourth quadrant, x's are positive or negative? Positive. And the y's are? Great. So we're done with the 45, 45, 90 reference triangles. Next up, let's draw or do the ones with the 30, 60, 90 reference triangles, but whose 30 is the reference angle. So when I talk about the reference angle, I'm talking about this one. So at 30 degrees, that makes a 30, 60, 90 reference triangle. Where 30 degrees is my reference angle. The ratio of side lengths for a 30, 60, 90 right triangle are a root 3, and 2a. Oops. Remember, the hypotenuse is a radius for our unit circle. So the radius has to equal 1. What does that mean that a has to be then? 1/2. So this side needs to be 1/2. And this side needs to be 1/2. Remember, the horizontal side is my x, and the vertical side is my y. So I can go back to my reference, or oh boy, Z, where did you go? My unit circle. Yes, Matt? Sure. Let's go over to the next spot where I can make a 30-degree reference triangle. And we'll copy in the same values there. And then again down here. I guess I should have gone ahead and wrote all the x and y coordinates negative in Q3. We already talked about that last time. Oops. And make all the y's negative, I suppose, here. Everybody's okay? The last set of angles here are the ones where I make a 30, 60, 90 reference triangle, but the 60 degrees is the reference angle. So I fill in my ratios of side lengths. Once again, I see that A has to be 1/2. So this side is 1/2. This side then has to be root 3/2. Again, the horizontal side is my x side. The vertical side is my y side. So if I go back to my unit circle, I can fill in. And just kind of keep going. So this would be 120. And I fill in the same values because I already took care of the signs last time we did this. Is everybody okay there? But you'll notice, Mr. Kulik, it still looks like there's like all these blanks left. What do you suppose all these extra blanks are for? Well, that's where I'm going to write the angle measure in radians. Oh, okay. How do I convert from degrees to radians again? Multiply by pi over 180. Excellent. So I'll just do that for you guys. That becomes 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, 7 pi over 6, 7 pi over, 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, and then 11 pi over 6. And we're all donezos now. You'll notice also in the content library I have one that's typed out for you with the same information on there. I rationalized the 1 over root 2 on this one that I typed out for you, since it felt like a final answer. So anyways, that's there, okay? All right, so let's do an example of like, okay, Mr. Kulik, yeah, we went and did all that crapola, like big whoop. What am I supposed to do with that? Here, let me show you how to use this. Let's do some examples. Actually, all right, let's say we're trying to do sine of 225. So what I do is I go to my unit circle and I look to see if 225 is on my unit circle. I found it right there. I remember that the unit circle is cosine comma sine. So the y coordinate is my answer. Notice I didn't have to draw anything at all. Ooh, can I see that again, Mr. Kulik? Sure. What if we have cosine of negative 60 degrees? Well, Mr. Kulik, I'm looking at my unit circle. I ain't seeing any negative 60 on there. And I would say, you're right. But do you see anything coterminal to negative 60 on there? Oh, what did coterminal mean again? How do I find an angle coterminal? You add or subtract 360. In this case, should I be adding or subtracting? Should be adding, because negative 60 is smaller than any unit or any angle on our unit circle. So I know this is the same thing as cosine of 300. So I'm just going to go and find 300 on my unit circle. There it is. And I remember that the unit circle is cosine comma sine. So cosine should just be the x-coordinate. Mr. Kulik. This guy is very nice. Notice, what do I not have to have memorized if I'm using the unit circle? I don't have to remember my 30, 60, 90 or 45, 45, 90 special right triangles. It's basically just condensed all that information into the unit circle for me. Woo! Doggy. That's nice.
Are you not talking about circle the last like tests and stuff?
No.
Okay.
Let's see. Let's do. Say we want to do tangent of 13 pi over 6. Oh, Mr. Kulik, a radian one? Why? Well, you could just convert the radians into degrees. How do you do that? Multiply by 180 over pi. Come on, people. When I do that, what do we get? 390. Well, that's bigger than anything on my unit circle, Mr. Kulik. Yeah, but is it coterminal to something? Ugh. So what should I be doing to that? Adding or subtracting? Since it's bigger than anything on my unit circle, I should be subtracting. Thank you. So it's the same thing as tangent of 30 degrees. Oh, okay. And I remember that I'll find 30 degrees on my unit circle. There it is. And I remember that tangent is y over x Everybody okay there? If I reduce that fraction, I end up with 1 over square root 3. And then if I rationalize my denominator, that's going to be root 3 over 3. What do you think? Can we handle using the unit circle? It's a pretty nifty tool. You'll get to practice it in the homeworks. You'll want to get good at using this. It's very helpful. You don't have to memorize it, but you do have to be able to use it. I have one more example problem, and we'll call our quitsies for today. Sound good? Too bad we're not doing any more math after this. You're just going to have to math on your own time. All right, so it says find the value of sine theta if cosine theta is 5/7 and cotangent theta is negative. All righty, Mr. Kulik. So I guess the first thing we're going to have to do is figure out which quadrant to put the terminal side of our angle in. But how do I do that? Well, I remember that cosine theta is equal to x, right? So I have really that, and I know cosine theta is 5/7. So I can say x is equal to 5/7. Or mostly what I care about is just that x is a positive number. What quadrants is x positive in? A 1 or 4. So I know my terminal side for my angle needs to lie in quadrant 1 or 4. All right, well, how can I reduce down any more than that? Well, I remember that cotangent is x over y. So I know that specifically x over y is negative. But I know that x has to be positive. And the only way for a positive divided by negative to give me a negative number is if y is negative. And where is y negative at? That would be quadrants 3 or quadrant 4. So where should my terminal side be located? In quadrant 4. Oh, okay. So I'll draw it like here. Everybody happy there? So I'm going to pick some point on my terminal side, draw in my reference triangle. I know that cosine is 5/7. I remember that cosine is x over r. So I can do that. Since my point is located in the 4th quadrant, I know that the x is positive. I've already written it that way. But the y has to be negative. And now I can just use the Pythagorean theorem to find that y coordinate. I subtract 25 from both sides. We'll square root both sides. To simplify a radical, I want to write that as factors of perfect squares. So the only perfect square divisor of 24 is 4, because 24 is 4 times 6, and the square root of 4 is 2. So this will be 2 square root 6. But this is the y coordinate in the 4th quadrant, so I know it must be negative. But now I have all the information I need. So I know sine of theta is y over r. So the y in this case was negative 2 root 6, and the r was 7. So I am done. What was really the most time-consuming piece of this? Making sure I got the terminal side in the correct quadrant. If you don't do that correctly, you're going to goof up the signs, the S-I-G-N-S's all over the place. I got to be careful when I say signs in trigonometry, whether we mean the positives or negatives, or the S-I-N-E's. What do you guys think? That's okay. So you guys can now be able to do 45 through 60. That's the end of the problem set, because this was the last section in chapter 2. That was quick, Mr. Cooley. Well, you should be happy. That means it's going to be like a little narrow little narrow test instead of a big wide test. Not that much to cover. Well, we have a couple of things to do before that. Okay. What haven't we done yet this chapter? Homework quiz. What might you expect next time? The homework quiz. Okay. We'll do some more practice in class. So I have a Delta Math assignment for you guys to work on, and then this worksheet 1 that's in the content library that we can work on both of those in class after your homework quiz. The following class we'll do the review, and then we'll be taking the test. What's today? Today's Wednesday. So we'll be taking the test Thursday then next week, I think. So the next class will be review and homework quiz and practice. The following class, which would be Tuesday review, and then Thursday would be the test. Elise?
It's 2.4.
No, I didn't put it on there. I'll just put it there. It might as well just be obvious. I guess that's fair. Instead of being like, oh, maybe.
Yeah.
That's not very helpful. So when you speak of me, speak well, right? Anybody else with questions or such? Cool. Stop.